a combination circuit. This combination circuit is a combination circuit because we have the elements of a series circuit along with elements of a parallel circuit together. So this is probably one of the more challenging circuits that you will see in 110 or 108, whichever course you're currently enrolled in. So I've got a little method I wanted to teach everyone. I call it the square, triangle, circle method. So the way I like to break this down so I can keep track is the first thing in the circuit we want to do is figure out what's the circuit's total resistance. And I'm going to start with the innermost parallel branch. So this is a parallel circuit. We can see that there's two paths for the current to flow in and out of the circuit, and these are the branches. So the first thing I want to do is find out what my branch resistance is. And so in this case, I know that 51 ohms and 39 ohms is going to give me a branch resistance of 90 ohms. And I'm going to make a square. Down here, I see there's just one resistor, so I know that it's 60 ohms. I'm going to not put in the ohms symbol. And once you hear, how did I get 51 and 39? Well, resistors in series, these resistors are in series, add. So now I have a 60 ohm resistor in parallel with a 90 ohm resistor. So I'm going to use my calculator. 90, 1 over x, plus 60, 1 over x, equals 1 over x. So the resistance, what I call the resistance equivalent for this, I'm going to put in a triangle. Well, so far we can make a little note here. Squares equal branch resistance. Triangles equal resistance REQ, resistance equivalent. So what I'm saying is that these two branches are equivalent to if I just had one 36 ohm resistor in the circuit. And then I go to the next level. So now I have a 41 ohm resistor in series with a 36, in series with a 23. And if I add all that up, it's going to equal 100. Down here I have a 73 ohm resistor in series with the 77 ohm resistor. If I add all that up, it's going to equal 150. So I have a 100 ohm resistor in parallel with a 150 resistor. That's what this branch resistance tells me. Same thing, 100, 1 over x, plus 150, 1 over x equals 1 over x. I come up with a 60. So now I know that all of this parallel circuit inside of this parallel circuit is equivalent to a 60 ohm resistor. I step out one more branch and, well, that's it. I'm down to the last part of figuring this out. So now I've simplified this circuit. I have a 22 ohm resistor in series with a 60 ohm resistor in series with a 14 ohm resistor. When I add all that up, I come up to 96 ohms. And using Ohm's law, I determine my current is 2.5 amps. So the law of a series circuit is that the current's the same. Well, I know these two resistors are in series, only one path. So right off the bat now, I know that the current here is 2.5 amps. I know the current here is 2.5 amps. And I know 2.5 amps is entering this branch and exiting this branch. Not sure how it's flowing yet. We're going to get to that here in a minute. An important thing we have to do is we cannot forget about how much the voltage that is being dropped at these series resistors on the ends. And by using Ohm's law, I determined I have 35 volts being dropped here, and I have 55 volts being dropped here. And what that leaves me with, and I subtract 35 volts, 55 volts from my applied voltage of 240 volts, what that leaves me with is 150 volts. So 150, I'm going to circle that. That's going to be, so a circle is going to equal the branch voltage. Meaning there's 150 volts. So the law of the parallel circuit says there's 150 volts being felt on this branch. There's 150 volts being felt on this branch. So at this point, I know the total resistance of this branch is 150, and I know that there's 150 volts. So using simple math, I know that I have 1 amp going through both these resistors because they're in series. And then that also allows me to make my voltage drop calculations pretty easy too. Since it's 1 amp, I know that I have 77 volts is going to be dropped here. 73 is going to be dropped here. Up here, we're going to have to do a little more work. But we do know one thing now. We do know that if 2.5 amps are flowing into this point and 2.5 amps are flowing out, we know 1 amp is going this direction. So I know by deduction 1.5 amps is going to be flowing through this branch. This resistor and this resistor are in series. So right away I know that there's 1.5 amps flowing through each of the resistors. Using Ohm's law, I can calculate how much voltage is being dropped at each of these resistors. It's going to be 61.5 for resistor 2, 34.5 for resistor 5. And since I started off with 150 volts being felt across this branch, when I subtract those two voltages, I should come away with 54 volts. And now I know I have 54 volts being felt across this branch, 54 volts being felt across this branch. Now that I know that information, I can go ahead and use Ohm's law, and then we can calculate what the currents are going to be in each branch. Once again, just like the lower circuit, if 1.5 volts is going into this branch, this parallel circuit, I know 1.5 has to be coming out. So by deduction, if 0.9 amps is flowing through this bottom branch, I know that 0.6 amps is flowing through the top branch. I can also check that by using Ohm's law. I know that the resistance of this branch is 90 ohms, and I know 54 volts is being felt across this branch. So I does equal E over R. If I do the math, I come out with 0.6 amps also. So it never hurts to double check and to look to make sure that the circuit makes sense. And once again down here, I know that 54 volts is being felt across this one resistor on this branch because it's the only resistor in the branch. And if I do, I equals, if I want to figure out the voltage, and I do I times R, 0.9 times 60, I will come up with 54 volts. So the numbers always check, and they always should. You should be able to look at the circuit and say, that does make sense. Double check your calculations different ways, and that's how you'll have no problem mastering the combination circuit.